Hello everyone, and welcome to a presentation on TigerScript. A TigerScript is a statistically typed beginner-friendly programming language designed by a team as part of 502 language and programming paradigms. TigerScript was created to explore and demonstrate concepts of compiler design and language interpretation. It's intentionally designed to be approachable for newcomers while still offering a solid structure for control flow, expressions, and variable management. Our Team 18, consists of me, Shivanath Samitapalli, Hruday Papisetti, Ronagrada, and Kshitij Akash. Can you please go through this? Like, yeah. Coming to the features of TigerScript, let's dive into the features that make TigerScript unique. First, it has a modular structure, meaning programs follow a clear sequence of declarations, expressions, and control flows. This keeps code organized and readable. It supports four fundamental data types: integers, float, strings, and booleans. Variable declarations are straightforward using the format, type, name, like in text, and of course, assignment uses equal to operator with support for compound operators like less equal to and minus equal to. Moving to the next slide. Continuing features of TigerScript Part 2. Continuing with expressions, TigerScript supports arithmetic operators such as plus, minus, star, slash, and integer division using double slash. We can actually compare values using equal to, not equal to, less than, minus, less than or equal to, and greater than or equal to. Logical operators like and, or not are also available. We also support syntactical sugar to simplify our code, such as increment and decrement operators, x plus plus and x minus minus, compound assignments, and ternary expressions like condition, question mark, true value, false value. For flow control, we support conditions with if and optional else, as well as loops while for. Finally, for code clarity, we have single line comments using hash and multi-line comments with slash star that end with star slash. Moving to next slide, declaration. Components of TigerScript. Let's talk about how we declare variables in TigerScript. The syntax is simple: type and name. For example, in text, float y, string s, bool flag. Here, each variable is declared with this type. This tells the interpreter to reserve space for the variable without assigning a value yet. Moving to the next slide, assignment. The syntax is variable underscore name equal to expression. This assigns a value to a declared variable. Examples include x equal to 10, y equal to 314, s equal to hello, flag equal to 2. The expression can be literal and arithmetic allocation or even another variable. Moving to the next slide, print statement. To output information in TigerScript, we use print function, syntax, print expression. You can print any expression, a variable, string, number, or even a result of an operation. It's useful for debugging and displaying final results. Moving to the next slide, while loop. Now let's look at loops, starting with while. The syntax will be while condition. The next will be code block. Here is an example: int x equal to 1, while x less than 5, print x plus plus. So this will print numbers 1 through 4. The condition is evaluated before each iteration, and the loop runs as long as it's true. Moving to the next slide, for loop. The for loop provides a compact way to iterate. Syntax: for initialization, condition, update, code block. Example, int x for x equal to 0, x less than 5, x plus plus, print x. This prints 0 to 4. The for loop includes initialization, a condition, and an update all in one line. That's all from my end.
Yeah, hi everyone. My name is Hruday, and in this video, I'm going to demonstrate about grammar. So let's look at the grammar for our TigerScript language. So to design any language, the first step we need to do is we need to come up with a proper grammar. So this is the grammar for our TigerScript language. So let's look at the grammar for program. So program is nothing but a statement list followed by dot. This dot denotes the termination of the program. And what do I mean by statement list? Statement list can be a simple statement or it's a statement followed by statement list. And when I say statement, it can be either declaration, assignment, print statement, expression, or all these things come under statement. And this is the grammar for declaration and assignment. For declaration, the type of the variable and then the ID, it's like variable name, and then the assignment. So ID followed by the assignment operator and then the expression or the value that we want to assign to that ID. And then expressions. There are multiple types of expressions that we are supporting in TigerScript. So here it is simple plus operation and then minus operation, times means a multiplication operation, and then division. So int div. So this divide, this does the floating pointer division, and this int div, this does the integer division. We support both of them in this language. And we also support logical operators like equal to, not equal to, less than, greater than. We also support not expression. And this is interesting. We also support ternary expression, and the grammar for ternary expression is the expression followed by question mark followed by expression colon and expression. This is how the grammar for ternary works in most languages. And then increment, decrement, compound SN operators also we support. When I say increment, the grammar for that is id followed by plus plus. So this is the one of the syntactic sugars that we support. So if we simply do plus plus, the value of that variable would be increased by one, and the same way minus minus value would be decreased by one. And when I say compound assignment, the grammar is like id plus equal to expression. So for example, if we want to increment value of any variable by 5, we can simply do plus equal to 5. This is one another syntactic sugar that we support in our language. And these are the four types of literals that we support: integer, float, string, and bool. And this is the grammar for print statement. It is pretty straightforward. So whatever we want to print, that should present in a braces. This is the left brace and this is right brace, and this is the print. And then coming to conditionals, so we support if else block. So whatever, so this is the grammar for if else block, and the here the else case is optional. We can write only if block without writing else block. That is also supported in this language. And whatever the code that is present, so for example, if this condition, if this expression evaluates to true, we need to execute some set of steps, right? And that should be present in a curly braces, and that is called as block here. And same for else also. After else, it should be followed by block of statements. And then coming to loops, we support two types of loops, for loop and while loop. And this is the grammar for both of them. And then I just explained about blocks. They should be present in curly braces. It is nothing but a statement list enclosed in curly braces. Now this is the grammar for the TigerScript. Now let's discuss about the lexer. Yeah, this is the lexer that we build for our language. So the basic purpose of lexer is to do lexical analysis. So to achieve this functionality, we are using PLY library. We are utilizing this library to do the lexical analysis. So the basic functionality of Lexer is it should take the TigerScript code as the input, and it should parse that code and split it into tokens. The output should be stream of tokens. And when I say token, these are all the known tokens. Like these are all the tokens that we support in our language. And these are some of the reserved words. These are also tokens. Now, I mentioned, right, like it takes the TigerScript code and it parses it and it converts each of them into token. So the way it does is it uses regular expressions to convert each and everything in the code into a token. It chooses all these regular expressions to do that. And for some of them, I have written in functions form, because for some of them I want my functions to have higher precedence than these regular expressions. For example, this comment, in any line followed by hash would be treated as comment, and this is for multi-line comment. This is for string literal, this is for number, and this is for id and new line. And we are, if there is any unknown token or illegal character present in the TigerScript code, then that would be identified along with the row number and also the column number as well. So we are handling the errors properly, that we can identify the row number and column number of the illegal token. And this is how the Lexa works. It takes the day, it takes the file, and the source file should be TigerScript file, and it takes the data present in that file, and it tokenizes it using the library, and then it prints all the tokens. So this is how the Lexa works. Now let's go to parser. So what this parse, the purpose of the parser is it should take all the stream of tokens generated by Lexer, and based on the tokens, it should generate the parse tree or abstract syntax tree in this case. So parser needs to know the grammar that we defined for our language. Based on the grammar, it it uh, eh, it processes the tokens and then it generates the abstract syntax tree. And so in our abstract syntax tree, like there would be multiple nodes and there could be different types of nodes possible. And if for a program, this is the grammar, like, as I explained earlier, it should know the grammar of our language. So here we define the grammar for program. So program is nothing but a statement list, and if there is a program, one AST node would be created and the type of that node would be this PRGM program. So this is one type of the node, and this BLK, this is simply block. So if we have any group of statements or we have statement list, that should be created inside a node of type block. And if we have a statement, this is the grammar for statements, and this is the grammar for expression. So for a single statement, it should be enclosed in node type CMD. And if it is a declaration, this is the grammar for declaration, and the type of the AST node should be DECL. And for assignment, the type of the node should be CMD. And we support all these print statements, we support these expressions, these comparison expressions, greater than, less than, equal to, all these things we have support. And for these types of expressions, the node type of AST node is EXPR, which is simply expression. And these kind of evaluates to a boolean value, and hence the type of the node is BOL, bool. And we support logical operations as well, and for these type of things also the node type is bool. And if it is a number, like number literal, the node type is num. If it is string literal, it is simply str. If it is boolean value true or false, it is simply bool. This is how the AST nodes would look like. And for ternary operator, the type of the node would be ternary. And this is the grammar for if. And if you look at this line, this is without the else block, and this is with the else block, and we need to handle both of these separately. That I am doing based on the length. Now again, this is for while loop, and this is for loop, and this is for update expression. Now here also we are doing the error handling properly. Like if anything goes wrong, then we print the line number where it went wrong. And then we support compound addition, compound subtraction, compound multiplication, and compound division as well, and compound integer division as well. So these are multiple things that we support in our language. And then yeah, this is how my parser works. So whatever the AST that this parser generates, that will be consumed by our runtime. That runtime will execute the program and generates the output. And my teammate Ronak will explain about the runtime.
Yes, thanks, Uday. So, hi everyone, my name is Ronak. Hey Uday, can you please share your screen? I'm not able to share my screen.
Yeah, sure.
Yeah, can you go to the runtime.py file?
Yeah.
Okay, hi everyone, my name is Ronak. So today I'll walk you through the runtime.py file, which serves as an interpreter for our own programming language. It works by traversing and executing the AST, which is abstract syntax tree, that is generated by the parser, and it actually gives the output of the code which is written by our own programming language. So the core of the logic basically lies in our runtime class. So let's go through each of the key components in this class. First, we have the constructor, which is defined by underscore underscore init at the top. So this sets up a symbol table using a dictionary. So it maps variables named to the runtime classes, just kind of like a memory in an actual computer where it resides. So there are two main methods which is present in the runtime class. First is the execute method and second is the evaluate method. I would like to go first with the execute method. So basically, the heart of this interpreter is execute class itself. It's a recursive tree walker, I would say, that handles different kind of AST nodes. For example, we have a node dot type, which is equal to command. So this blocks, and we have one more which is node dot children dot type double equal to print. So this block handles the all the commands like print, if, while, for, etc. So this tells the interpreter basically that if a print statement is encountered, evaluate the next node and print its results. So this is what the node type command and all the childrens of it, print, if, while, for, actually does. Now, if we go to the if part, which are the conditionals, here the runtime actually checks the conditions and executes the appropriate code, based on the result. It even handles the else block, if they are present. If we go down a little bit to the evaluate method, so here actually all the uh, computations happen inside the evaluate method. This method is responsible for processing all the expressions. For example, if you look at line number 72, node dot type, which is double equal to expression, we have our left output and the right. This pattern handles, binary expressions like plus b or x into y, for example. The interpreter evaluates both the operands recursively and, then applies the operator. So it also handles the logic for booleans and even the ternary operations. Now the main part is the compound operators. Here there is actually a smart handling going on. Here I didn't had to explicitly write any code for handling the compound operators like plus equal to, star equal to, minus equal to. That's because the parser automatically converts something like, for example, x plus equal to 1 into an expression node x equal to x plus 1. And this thing is already handled in the parser. So all the syntactic sugars, just like compound operators, we don't need to explicitly write the code. Our parser is smart enough, to convert it into an actual code and, run it behind the scenes. And also, if we take the example, yeah. So if we go to the entry point, can you go a little down?
Yeah.
So lastly, this is our main function that acts as the entry point using the script. So here it reads the source file and it builds the AST, runs the interpreter. So, and yeah, that's it. Yeah, thank you so much. Kshitij, would you like to go next?
Yeah, thank you, Ronak.
Kshitij, you should be able to share your screen now.
Yeah,
Can you?
yeah, okay. So yeah, hi everyone. My name is Kshitish, and like I'm giving a demo for the sample program and explain the sample program. So let me share my screen. I hope my screen is visible.
Yeah, it's visible.
Okay, so let's go to the sample two. Here you can see like we implemented different types of for loop, and like it shows a different type of update. You can see the normal updates like the x equal to x plus 1, same as the decrement. We also support the postfix increment and as well as the decrement. Simultaneously, we also support the compound increment and the compound increment. You can see we implemented a different for loop. This is for the case one, x equal to x minus 1. This is for the postfix decrement. This is for the compound x minus equal to 1. Similarly for the similarly for this x equal to x plus 1 and like this. Let's run the sample too. Yeah. So here you can see the output for the different sets. These are the 6 sets. Among them, the 3 are for the increments and the 3 are for the decrement. And let's go to another sample file. Yeah, here you can see the different sample files. This particularly shows the different type of ternary operator. So this test validates assigning the ternary results to a string and the int types. Also using the ternary directly in a print statement, embedding the ternary inside a larger expression, and nesting a ternary operators. Uh, you can see the different type of cases like this case one, case two, case three, case four, and something. Yeah, like this. Let's run this file. Yeah, you can see the output here. For this case one, you can see the y is greater. For this case two, false. For this case three, 6. And like as you see the other outputs here, x is a smaller and the y is greater. So that is for the ternary. We implemented different sample programs. You can see here, these are the total 10 sample programs. So we can run any programs and it's working perfectly fine. Let's I think yeah, that's it from the code perspective. And let's can you Uday, can you share the PPT again? Yeah, let's go to the future scope. Yeah, so for the future scope, we are planning to implement advanced data types such as arrays and object functions, as well as we are also planning to improve the error handling for our runtime code, as well as we are planning to support the external files such as reading and writing from the external files, as well as the database interactions. And I think yeah, that's it from our side. Yeah, thank you.
Yeah, thank you everyone.
Thank you. Thanks,
Okay,
everyone.
thank you so much. Thank you.